Now, the next one that we're discussing is the urea formaldehyde. So, urea formaldehyde. Now, as the name suggests, it is indeed a combination of urea with formaldehyde. So, we draw urea first, that is NH2 C double bond O, NH2, and this is combining with formaldehyde, which is represented as HC double bond OH. Now we already know how the combination proceeds, so this is urea. And now when the combination proceeds, we get NH2 C double bond O, NH, CH2, OH. Now imagine another one of these coming in contact with this, so NH2 C double bond O, NH, CH2, OH. Now we know when this type of situation occurs, we lose an OH from here, we lose an H from this NH2, and once we lose them, so let us just make some changes over here. And now we have CH2 lost from this side, and we have NH remaining at this side, and let us say that they form a bond between them, and this is how the polymer goes on to further step growth chain that we've already discussed, and this is how the chain grows onto a long polymeric chain. So this was urea formaldehyde, and as the name suggests, you can already note down the two monomers that we're using, that is urea and formaldehyde. Now moving on to the next one, we have a new topic ahead of us, and this is known as biodegradable polymers. Now, as the name suggests, they are indeed biodegradable, that is, they can degrade on their own. Now, what was the requirement of these polymers was because the previous polymers that we developed with using the copolymerization, homopolymerization methods, polythene, polypropylene, and such were causing a lot of pollution. So, in order to stop that, we wanted some polymers which can degrade on their own, and also in when you see in hospitals that when we put stitches on patients, we used to use nylon 66, which was not a degradable polymer. So inside the body, we wanted the polymer to degrade itself on its own, and that was why we were looking on to some new type of polymers that led to the formation of biodegradable polymers. Now, biodegradable polymers, so we'll be doing the example. So the first one that we'll be discussing is formed of two monomers, that is beta hydroxy butyrate. So beta hydroxy butyrate in combination with co beta hydroxy valerate. Now let us draw the two monomers. So beta hydroxy butyrate looks something like this. So we have four carbon, and so at the beta position, which is this position, we have OH group attached, that is the hydroxy group. This is combining with beta hydroxy valerate. Now beta hydroxy valerate is a little different from the previous case, that is butyrate, only the number of carbon atoms. And here at beta position, again we have hydroxy group, that is the OH group. Now these two will combine, and how will they combine? So what happens is this will lose an OH, the other one will lose an H, and this will lead to the formation of our polymer. Now we know H is lost, OH is lost from the other side, and let us now draw the polymer. So it will be O, this chain coming from above, C double bond O, we have O again, we have C double bond O, and we have this chain extending here. So n number of this, because of the formation combination of two monomers, that was beta hydroxy butyrate, beta hydroxy valerate. Now since we are forming many of these, so the addition of poly, and this completes the name of the polymer. So the polymer itself is called polymeric beta hydroxy butyrate, co beta hydroxy valerate, and in short form, we call it PHBV, a very common biodegradable polymer that we all might have seen. Now, moving on to the next one. So, the second biodegradable polymer that we'll be discussing is nylon 26. Now, up till now, we have discussed a lot of nylon polymers, and in all of them, they were not biodegradable. Only this one is, and it is formed by two monomers by species again. This is CH2, C double bond O, OH. Now, the name of this monomer is glycine. Glycine over here is combining with another monomer that is called aminocaproic acid, and it is represented as this NH2, CH2, whole 5, C, double bond O, OH. This is aminocaproic caproic acid. Now, both of them on combination, what happens is we know that they'll be losing a water molecule, and therefore this is called copolymerization. And here we have NH. Now H, another H is lost because we needed to open the chain. CH2, C double bond O, NH, CH 25, C double bond O, OH is lost, and we have N units of this. So N, both of them are combining to give us nylon 2,6. The 2 suggests that referring to the 2 carbon atoms from glycine, and the 6 referring to the 6 carbon atoms from aminocaproic acid. So this leads to the formation of nylon 2,6, which is a biodegradable polymer. Now the last one that we have is, so glycolic acid is combining with another monomer that is lactic acid. So both of them are combining. Now glycolic acid is represented as OH, CH2, C double bond O, OH. And lactic acid is represented as OH, CH3, H, C double bond O, OH. Both of these on combination, on polymerization, gives us our polymer, which is, now O is opening from this side, we know. H is lost to another molecule perhaps. We have C double bond O. Then we have O, CH3, H, C double bond O, and OH is removed from this side, and we have N, N, N. So we have got two monomers, glycolic acid and lactic acid, combining together to form a polymer. This is the third type of biodegradable polymer, and the name of this is polyglycolic acid, polylactic acid. So this is our third biodegradable polymer that we discussed. So this is polyglycolic and polylactic acid, and this is a biodegradable polymer. So this brings us to the end of polymer chapter.